All right, so in this one, I want you to try this question. It's a multiple choice question. It says, which of the following series converges, are conditionally convergent? That means the series converges like it is, but if I take the absolute value of the sequence terms, so I'm just always adding those terms of the sequence, I take away the minuses, if that needs to diverge, but the original series needs to converge. So I'm going to look at each one of them. My answer choices are, it's either just 1 and 2, 1 and 3, or 2 and 3. So let's see if number 1 is conditionally convergent. So I'm going to take away the negatives. So take away the alternating part. I just get 1 over n to the 4th. And I know that converges. That's a p series where p is greater than 1. So if the absolute value of the terms converges, that's absolutely convergent. So it's not conditionally convergent. We're looking for which ones are conditionally convergent. So anything with b, or anything with 1, take it out. Oh my gosh. So look at that. It's just d. Well, that was not intentional. All right, so let's look why the other ones are conditionally convergent. So supposedly 2 and 3 both be conditionally convergent. Means the take away the negative version, and that is the harmonic series. We know that diverges. But we know that the alternating harmonic converges. So yeah, that's why 2 is conditionally convergent. This converges, but the absolute value does not converge. This one, it's an alternating series. So if it's an alternating series, each term is getting smaller. 1 over, I could look at a to the n plus 1 over a to the n would be 1 over cube root of n plus 1 over 1 over the cube root of n. And that is going to be less than 1 because this number up here has a smaller or a bigger denominator, making the overall number smaller. So it's decreasing, and the limit as n goes to infinity of 1 over n is equal to 0. So the alternating series converges, but if I take away the negatives and I just look at the absolute value, I'd get 1 over n to the 1/3, and that is a p series that diverges because the p is less than 1, less than or equal to 1. All right, so that'd be D. All right, these last two are a little tricky, and I'll explain it the best I can. It says, find the values of x that make the series converge absolutely. All right, so what we're going to do is we want to make this converge absolutely. So we want that to go away. And what we're going to actually use is the ratio test. So I know using the ratio test, I just do the absolute value of that. So I'm going to say the limit as n goes to infinity of the absolute value of a to the n plus 1 over a to the n. Using the ratio test, this thing will converge if that's less than 1. So I want to force this thing to converge. So I'm going to say the limit as n goes to infinity of the absolute value of the n plus 1 term. So this, I'm looking at absolute value, so I'm going to take away the alternating part. And I'm just going to look at the n plus 1 times x plus 4 to the n plus 1. I'm looking for the x number that would make this converge absolutely. So I'm going to force it by saying, okay, well, let's find the limit. Let's find the x number where the limit of the n plus 1 term over the n term is less than 1. And then we'll find all the x's that would make that work. It's over 6 to the n plus 1. That's the a to the n term. And I divide it by the a to the nth term, so it'd be 6 to the n multiplied by the reciprocal, x plus 4 to the n. And I want to solve for that less than 1. I need more room. I should have written smaller. so we're solving this. All right. So now it's when we rewrite the terms. The n plus 1, can't rewrite that, but I can rewrite x plus 4 to the n plus 1 as x plus 4 to the n times x plus 4 over 6 to the n times 6 times 6 to the n over n x plus 4 to the n. And I'm finding for what values of x would make that limit as n goes to infinity less than 1. All right. So now I'm going to cancel some stuff out. Actually, that cancels out, this cancels out. And I'm going to rewrite this again just to make it as clear as possible. N plus 1 over n. I've got x plus 4 over that. I got to find what values of x would make this less than 1. Now this part I'm going to look at as the limit goes to infinity for n. As n goes to infinity, what are we left with? We are left with the absolute value of x plus 4 over 6. Because as n goes to infinity, if I do infinity plus 1 over infinity, that's basically 1. So that's gone, n's are gone, and I'm left with this absolute value inequality. And I can solve that by saying, okay, well, x plus 4 over 6 is less than 1, but greater than negative 1. And then multiply everything by 6. And then subtract 4. So these are the values of x from in between negative 10 and 2, not including those numbers. So if I plug those in, this over here would be absolutely convergent. It would converge absolutely. So if I picked a number, I don't know if I want to do that. Pick a number like 2 is in there, right? This would be a 2. So it's saying 6 to the power of n over 6 to n times n. That alternating series would converge absolutely. All right, that's all I want to say about this one. I'll say some more in the next one. Okay, I just plugged in 2, and it was kind of throwing me off. That's wrong. So if I plugged in 2, okay, let's just say it now. If I plug in 2, I was being kind of careless. On the next one, I'm going to show you, and I've actually thought about this one out. But this one, if I plugged in 2 for x, I'll be left with this, right? But those basically cancel out, and I just have this series of negative 1 to the n times n. So it's like 1 minus 2 plus 3 minus 4. That thing is going to diverge. So that's why it only converges absolutely for x's in between negative 10 and 2. Numbers at the endpoint, at 2 it would diverge. At negative 10, it probably would also, but I don't want to look at that right now. All we care about this question is in between, if x is in between negative 10 and 2, it converges absolutely. On the endpoints, at 2, at negative 10, it could converge conditionally or diverge. And then numbers past that, like numbers bigger than 2, numbers less than negative 10, that's going to diverge. It's going to make the series diverge. All right, so I've thought about this one a little bit more. We're going to talk about the endpoints on this one. All right, so we want to find the values of x and make this converge absolutely. So this first part, I want you to pause the video, try it on your own, see how we did the last one, and try to recreate the steps here. But what we're using, okay, pause, unpause. We're using the ratio test, and we know it converges if the a to the n plus 1 term over the a to the n term, so if the next term over the term before it, if that limit as n goes to infinity, if that's less than 1, the series converges. So we're going to force it into converging. So what I'm going to do, I'm going to write smaller this time. I'm going to use this. So I'm going to say the limit as n goes to infinity of the a to the n plus 1 term would be x minus 1 to the n plus 1 over n plus 1 times the reciprocal of the n term, so just undo that. Where is that less than 1? Let's solve for the x's that make that less than 1. So the limit as n goes to infinity, x minus 1 to the n times x minus 1 over n plus 1 times n over, when is that less than 1? So these cancel. The limit as n goes to infinity is going to make that part go away. So I just have x minus 1 in absolute value is less than 1. Because as n goes to infinity, n over n plus 1 is just 1. So now I say, well, x minus 1 is less than 1, greater than negative 1. Add 1 to everything. It'd be 0, and then 2. So my series converges absolutely for this interval. So if x is anything bigger than 0, if x is anything less than 2, if I plug in that x to the original x, that series that we create would converge absolutely. Okay, at the endpoints, at x equals 0, at x equals 2, it could converge conditionally or it could diverge. Any values of x less than 0, any values of x greater than 2, it'll diverge. All right, so let's look at when x is equal to 0. So if I plug in 0, I get 0 minus 1 is negative 1 to the n over n. This is a harmonic, an alternating harmonic, which we know now converges. So that means this would converge conditionally when x is equal to 0. It doesn't converge absolutely because it only converges absolutely whenever x is bigger than 0. We just kind of proved that in this last thing. So at x equals 2, I plug in 2. 2 minus 1 is just 1. So I've got 1 to the power of n, which is just 1, over n. And that is a harmonic series that diverges. So if x is 2, that would make this infinite series diverge, period. If x was equal to 0, that makes this same infinite series converge conditionally. It would not converge absolutely, because remember, if I take the absolute value of this, that would be a normal harmonic, which diverges. All right, so a little thing about the endpoints. So when you find these numbers, so like number less than x less than the number, so the numbers in between, not including the numbers of the endpoints, it would converge absolutely. At the actual end numbers, like the cutoffs, it could converge conditionally or diverge. You got to test it. Then anything after that would just diverge. All right, that's it for this video. If you have any questions, make sure you ask me next time I see you in class. And thank you for watching. Hopefully it helped. Bye.